while the slides are being put up, it's my pleasure to introduce the next speakers, Sebastian Clermont and Laurens Potzenheim. And Sebastian, Laurens, floor is all yours.
Thanks, Peter, for the introduction. My name is Sebastian, this is Laurens. And together with Samet Dützli, Christian Jansson and Patrick Struck, we have looked at sanitizable signature schemes and how you can instantiate this primitive from lattice assumptions. So first, let me introduce the sanitizable signature scheme, which is a less popular variant of the signature. The sanitizable signature scheme starts off just as a signature that you know. So you have some key for a signer that uses a secret key to sign some message. Now this is the point where the sanitizable signature becomes interesting, because now you also have a sanitizer, and the sanitizer also has its own public and secret key. And the sanitizer can now create modifications of this initial signature to create a sanitized message. For the sanitizable signature to work, the signer needs to include some additional information into his signature. So at signing time, the signer needs to specify which modifications are allowed to be performed by the sanitizer. So the sanitizer cannot modify all parts of the message, but only the predetermined parts that the signer has specified. And the sanitizer also has to be specified in advance by providing his public key. Now for the sanitizing step, the sanitizer needs to have access to the original signed message, and then can perform his modifications by providing some modifying instructions that should be admissible under what the signer specified as admissible modifications. And he needs to provide his secret key to then output some sanitized message where parts of the message have been modified. There's some standard security that you would expect from these sanitizable signatures. The first one is kind of obvious. You still want the unforgeability that you get of regular signatures, but then it starts to get different. So you want accountability, but not from the signer and the sanitizer as a pair, but you want to have accountability of either the signer or the sanitizer, so they cannot blame each other for a signature later on. And you want the sanitizer to only be able to modify these blocks that the signer has specified in advance. So when starting to see how we can instantiate this in a post-quantum setting, we did some literature overview of constructions that have been brought forward in the classical sense. And we've seen very different constructions that have been introduced. There is some constructions that would be fairly forward to instantiate from lattices using only digital signatures and public key encryption, such as the one brought forward by Fischlin and Harasser. But this one's unfortunately not very efficient to instantiate in the real world. Then there's some instantiations that hinge on the so-called Chameleon hash function, which I will talk more about later, where we are somewhat close, but there's a missing gap, which Laurens will talk about in a moment. And then there's signatures that hinge on more specialized building blocks, like the accountable ring signature or the equivalence class signature, for which no lattice-based constructions exist at the moment. So in our paper, we looked at these constructions using Chameleon hash functions where we are close, and tried to close this gap to be able to instantiate them in practice. So you might wonder now, what is a Chameleon hash function? A Chameleon hash function is basically a hash function that allows for finding collisions on the hash function. So it's a public key primitive, and you have a public key as well as a message, and you get output a hash and some randomness that you need for verification. This is like a normal hash function. And then you have this adapt function. This adapt function now takes a secret key, the original hash, the original message, the original randomness, and you give it a new message, and for this new message you want the hash to be the same. And this adapt function now gives you some new randomness under which you have a collision on the hash function. And then last, you have a check algorithm where you can hand in the public key, the message, the randomness, and the hash, and see if this hash is valid for the given arguments. So now how I will show you a very basic construction so you get an idea of how you can use this Chameleon hash function to construct a sanitizable signature scheme. So here you have a message consisting of 7 blocks, and as I've introduced in the beginning, you have some blocks that are admissible, these are orange, and you have some as admissible for modification, meaning the sanitizer can later perform modifications on them, and you have these blue blocks that are fixed and are not supposed to be modified by the sanitizer. So when signing, what the sanitizer does is for the blocks that he does not want to be, it should not be changed by the sanitizer, he just signs the messages as is. And for the blocks where a modification by the sanitizer is admissible, he does not sign the message directly, but first uses a Chameleon hash function to get some digest, which he then signs. And for this Chameleon hash function, he has to use the public key of the sanitizer so that the sanitizer can then later do modifications. So the modifications would look like this. The sanitizer would take the signed message, do his modifications, and then run the adapt algorithm of the Chameleon hash function to get some new randomness. And as such, the hash values that have been signed by the original signer, they remain the same, and as such, the signature continues to be valid and is now sanitized. For this to work, we need some security properties of the Chameleon hash function. First of all, and this is the tricky part, we want a collision resistance when collisions are known. So during sanitizing, the sanitizer gets some collisions on the Chameleon hash function, which are then published as part of the sanitized signature. And we want the Chameleon hash function to be still secure if one set of collisions is known, or in fact any pair of collisions, as you can do as many sanitations as you want in this primitive. And then additionally, you want the indistinguishability of the output of the adapt function and the hash function, so you do not want it to be obvious if the signature has been modified or not in the sanitizable signature sense. Another big question is, how do you build such a Chameleon hash function from lattices, which is where I hand over to Laurens.
Thank you. All right. So our starter for constructing such a Chameleon hash function was the so-called bonsai hashing, which is basically just iter hashing, but with a trapdoor in it. So basically what happens here with a hash function is we just have a matrix AB, and then multiply some short vectors onto that to get some output H, the hash H. And then if we have a trapdoor in there, we can use the so-called pre-sample algorithm to find a new randomness E prime. This is collision resistant, so normal collision resistant, because if you have a collision, this collision produces an SAS solution, as you can see here. The only issue with this hash function, or with this Chameleon hash function, is you cannot reveal collisions to an adversary. Because if you reveal these collisions to an adversary, or multiple of them, then an adversary could build a short basis for the lattice. Well, yes, it's a bit longer than before. It's still a short basis, which is not good. So at least we can't do the reduction. So we have to find something else. The next construction that is in the literature is a tag-based Chameleon hash by Li and Liu, which works in kind of a similar way, but avoids showing an adversary a basis, basically. Because what they do is, for each message, they generate a new B. They do this with the random oracle, so they put a uniform Z into the random oracle together with the message, and then also some tag to generate a new B, and then they do this multiplication of a short E with the matrix. Then for adapting, if you have a new message, you calculate a new B, and then again use the pre-sample algorithm. The good thing now is that since we have different Bs, we don't reveal this short lattice, this short basis, sorry. And therefore, they can show that this is actually collision resistant even when the adversary sees collisions. However, it is a tag-based Chameleon hash. And the SSS construction that we use don't use a tag-based Chameleon hash, but only a standard Chameleon hash. So our first idea was, what happens if we just ignore the tag? Well, it's not secure anymore, who would have thought? The issue now is if you ignore the tag, then if the adversary just calculates some hash, then asks for a collision, because he has a collision oracle, and if he then multiplies this collision that he has seen with 2, this is a new collision. So you have this 2h, the 2e, and the 2e prime, and this is a collision for a new, not seen before 2h, and therefore this is a forgery or a collision, a new collision, which then breaks the security game. But what we did basically is we looked at this construction and then modified this construction to get really full collision resistance. Because in essence, what we notice is that the E on the left side you see there is a bit free. You see that the E is just chosen from some distribution, some short distribution, but it's not really doing anything really except for then you being able to be pre-sampled also. So what we did to construct a now fully collision-resistant Chameleon hash is to use a trapdoor commitment scheme to bind this E to make it not so free. So instead of choosing the E after the B, what we do is we choose it beforehand, and then commit to it, and then put the commitment into the random oracle to also make the B dependent on the committed value. Yes, this then does not, or this prevents this ×2 attack because the adversary is not freely allowed or cannot really multiply this because then the commitment would change and so on. So he would have to find, or he would have to break the binding of the commitment scheme. Yes. We do need a trapdoor commitment scheme for that, so not only a normal commitment scheme, because in the end, in the adapt algorithm, we also have to change or be able to change what is in the commitment. You can see here this with this trapdoor open algorithm, but apart from that, it's relatively easy. You can show full collision resistance for this hash function. I won't show it to you because it's a relatively complicated proof, but it works. Now, we still have a problem because if you run the adapt algorithm twice for the same inputs, you get 2 different randomness values out of there. This breaks the so-called uniqueness property of the Chameleon hash, and the bad thing is that uniqueness is often required for the accountability and unforgeability of SSS constructions. So we needed to fix this problem. So what we did is we took a certain transform by BLLR MST19, where they basically say if you have a sanitizable signature scheme without accountability, you can add a verifiable ring signature to that, and then you get a SSS with accountability. Yeah, the only problem then was that for this transform, you need the verifiable ring signature, but there was no verifiable ring signature from lattices yet in the literature. There were some claims, but we weren't really able to confirm these claims. So what we did, we constructed a new verifiable ring signature from lattices. Yes. Oh, by the way, a verifiable ring signature, for those of you who don't know, is basically it's a normal ring signature, but after signing, users can claim or deny authorship of a signature by publishing some new value, basically. Yeah, and then as I said, we constructed the VRS generically. We used some kind of special tags and also NISIX, and then instantiated that with lattices. And then you can see here on the bottom, basically, so what we have these generic SSS constructions, then we put our Chameleon hash into there to get a weak sanitizable signature, and then we put the VRS on top of that together with the transform, and then get a really strong, secure sanitizer signature out of that. Yeah, so in total, we constructed this fully collision-resistant Chameleon hash, also constructed a lattice-based verifiable ring signature, and with that, we now have lattice-based SSS in the random oracle model, and they are secure. The only issue now, or the open questions now would be, is there any lattice-based Chameleon hash with uniqueness, which seems a bit difficult to do because due to the usage of pre-sample, it's kind of inherent that it breaks uniqueness. And also maybe is there a direct SSS construction, because right now the construction is not really efficient, so it's more really of a theoretical interesting thing, but not for practice yet. Yeah, and if you want to look at the paper, here it is. Yeah, and that's it.
Thank you very much to both of you for the very nice talk. Are there questions for Sebastian and Laurens? Yeah, please, Mike.
Hi. How the efficiency changed with this ring signature edition? Because previously it's pretty obvious, like you do the hashing of these parts, then you run the signature, and then for the sanitizer you only need to find a different input to the hash function there. And with this ring signature edition, how is this affects the efficiency of the total construction?
It makes it worse, and by a lot. So we didn't look at numbers because it only really was interesting for the theoretical part. So we have to say that the construction of this weak SSS already is not too efficient already. So the example that Sebastian showed you, that's only a very basic SSS. You typically want some more security, so you need more advanced or more complicated constructions. But the addition of the verifiable ring signature is really not so great. So you really want to get rid of it. So you want uniqueness or something else to get a fully secure SSS. Yeah, but I can't tell you really any numbers. Think like maybe double, maybe even triple, depending on the NISIC that you use. Because so while the statements that you have to prove with the NISIC are not too complicated, it's still a NISIC and lattice-based NISIC. So yeah.
Any other questions? Please.
Hey, you mentioned you develop your own lattice ring, or verifiable ring schema. How does that compare to the existing ones out there that are compatible with lattice-based assumptions, like Liu V ring or ring Tesla, something like that?
I am not too sure, to be honest. So we didn't really try to find parameters to instantiate it. And I also don't know too much about it, practical instantiations of ring signatures, so I would have to look it up. Yeah.
Any other questions?
I'm not an expert in this field, but I'm curious about, can you go back to your slide a little bit?
Which one?
Maybe Chameleon hash. Oh, the next
This one?
This one.
Uh-huh.
I'm just puzzled about the random oracle mu prime z prime commit 0.
Yeah.
Why 0 here? Like.
Yeah. What we basically want to do there is to put an empty commitment into the random oracle, because the issue is if you want to compute the E prime, for computing E prime, we already have to know the B, but the B uses the commitment. Therefore, and the B depends on the output of the random oracle, but the random oracle depends on the commitment. So if you would want to put the E into the commitment, you would have the circular requirement, which is not possible. And this is why we need the trapdoor commitment, so that we can first commit to an empty, or put an empty commitment or commitment to 0 in there, and then only afterwards put the real E prime into there.
Okay, I don't see further questions, so please join me in thanking Sebastian and Laurens again. And then we now have the talk that is pre-recorded at the end of the session. Yeah, so you'll fire up the video, right? Okay.
Good morning, everyone. Today I'm gonna